So we will continue to the next talk. And the speaker is Professor Gilbert, and she graduated from Princeton University. And she's now the Herman Goldstein Professor at the University of Michigan. And she received the CMSA Ralph Kleinman Prize in 2013. So let's welcome the Professor Gilbert.
Thank you. It's a pleasure to be here. So at this conference, we've heard talks about economics, political science, public health, cryo-EM, phase retrieval. I'm not going to talk about any of that. The problem I'm going to talk about is, I hope, a fundamental problem in data analysis, and it's how to clean up your data in a certain way before you do any kind of analysis on it. So, right, these are not algorithms that will help you solve any important problem in social science or imaging science, but hopefully it will help you clean up your data so that you can then begin to do much more sophisticated algorithms. And so I'm going to talk about a problem which I have termed metric repair or sparse metric repair. And we're going to talk about applications in repairing manifolds and in graph metric repair. So this started out as joint work with my postdoc, Lala Jain, and has morphed into many more projects with my student Rishi Santalia, and then a whole group of folks at UT Dallas. Okay. All right, so I'm going to begin with the idea that you've got data that come from some metric space, and your data has been corrupted in some way. It's noisy data, or you've collected data, but various important elements are missing in it. It's just garbagey. And it's garbagey in a way that the geometry of the underlying space where you think your data lie has been distorted in some way. Okay, so Frank, here you go. So, imagine your data is supposed to be in this nice space, but instead parts of this space have been warped or distorted. And so you should imagine that these are distorted triangles. So at dinner we were talking about flat Earth versus a regular Earth. So there we go. We've distorted space in some way. Okay, so here's the setup of the problem. We're given similarity data or distance data. Let's call this D prime, and it's supposed to adhere to a metric, right? It's supposed to satisfy the triangle inequality. It's supposed to be nice, clean data, and in particular, if your data is a metric or satisfies all the properties of a metric, if your distances satisfy the metric properties, then all sorts of other machine learning data analysis algorithms are really nice. So you can run downstream unsupervised machine learning algorithms much more successfully. Things like clustering, you get much better, you get approximation guarantees for very important graph algorithms like traveling salesman or minimum spanning tree when your distances satisfy a metric. There are all sorts of applications in computer vision, such as image retrieval, and in computational biology, where your algorithms are cleaner, simpler, come with straightforward guarantees when your data satisfy a metric. Okay, that should beg the question, how do we ensure that our similarity data actually satisfies a metric? Right? Well, seems like an important point to check before you do any sort of machine learning algorithms. Okay, so now I'm going to give you a crash course refresher in what does it mean for the distances to satisfy a metric? So that means that if I have a matrix of distances, or say similarity, or the converse dissimilarity, it is said to satisfy a metric if Well, the distance from any point to itself is 0. And so it should be a symmetric matrix. The entries should be non-negative. The entries on the diagonal should be 0. And we should satisfy the triangle inequality. OK. That's the triangle inequality. This is a bit of a mess to encode all of that. So I'm going to focus on the triangle inequality part and rewrite it as a system of inequalities. I'm going to rewrite it as this very structured, tall, thin matrix M times the vectorized form of the matrix D. And that should be entry-wise greater than or equal to 0. The matrix M here encodes all these triangle inequalities. It has, in each row, it has 2 1s and 1 -1. All the rest are 0s. And it's basically saying this inequality should hold for my distances, for any triple of distances. OK, great. What? No. It has to be non-negative. No. I want to make sure that this guy plus that guy minus that guy is greater than or equal to 0. OK, good. Check. OK, so I'm going to state the metric repair problem formally. OK, so suppose I'm given a corrupted distance matrix D prime, i.e. some triangle inequality is broken. I would like to find a perturbation to the corrupted distances so that I repair the distances, so that I change a broken triangle, I repair a broken triangle, and make sure that then that the resulting distances satisfy a metric. OK? And OK, there we go. P is the repair, D prime is the corruption. In math, in more theoretical math papers, they often begin by saying fix something or other, fix x to be blah. Here, I don't want to use the word fix. I want to use the word repair instead. OK, good. Mathematician's joke. Excellent. OK, so traditional techniques for solving this problem. It was actually first formulated explicitly in a paper by Brickell et al. In about 2007. And they said, let's find the perturbation by projecting onto the space of matrices that satisfy metric, and let's find the closest point in the Frobenius norm. OK, so like minimize the L2 error. OK. Project onto the subspace of metrics. You could also change the space onto which you project a little bit, and then you can go back further in the literature. You can consider this as an example of multidimensional scaling, or go look at this in the psychometric literature if you project onto the cone of Euclidean distance matrices. So that is like insisting that you repair to a Euclidean distance as opposed to any generic metric. OK, maybe you want to make sure your points, you sort of are repairing Euclidean space. Actually, there's a really cute algorithm that's just works in R3 that was come up with by the computer scientists. So there's a randomized algorithm for repairing broken triangles. Come up by Berger et al. It's kind of a cute example. You could also view this to some extent as related to rigidity theory and go back as far as Cauchy. How many sort of edges of a polygon do you have to change before it becomes degenerate? The problem with all of these techniques is that they perturb most of the distances. So you take a data set, or you take a set of distances where just a few of them just a few of the triangles are broken, and yet you're going to adjust many of the distances. That just sort of seemed wrong to me. That seemed like you're damaging your data set too much by doing this. And so I wanted to take a more optimistic approach, which was to assume that most of the distances are correct, and only a few of them are corrupted, okay, which leads to quite a different problem, which is to minimize the number of changes that you have to make so as to repair to a proper metric, right? Instead of asking to minimize the distance to a proper metric, make as few changes as possible, so minimize the L0 pseudonorm of the perturbations, right? It seems like a completely reasonable thing to do. And if you had been paying attention to the last 15 years of sparse problems, you would say that is a non-convex objective function, and the thing that I should do is relax to a convex objective function and minimize the L1 norm of the perturbation subject to it results in a proper metric. That's really tempting, but don't do that. At least don't do it naively, because in fact, it doesn't give the sparsest solutions. If you code it up, it doesn't work very well in general. And those of you playing along at home and really on the ball will note that M is tall and thin. It's overdetermined. It didn't look at all like the matrices in the third example of David's high-dimensional linear regression. And it's not a particularly incoherent matrix. So this is really not a good thing to do. At least naively, it's not the right thing to do. I don't suggest that you do it. OK, now I also have not a real problem, because I know the answer, but I do have something to point out about trying any sort of convex method for solving this problem, and that is there are an awful lot of constraints. So if I want to minimize whatever kind of objective function subject to all of these constraints, there are like roughly n-cubed triangles, n-cubed constraints coming from each triangle inequality. And however good a job these convex relaxations do, solving these large linear programs is computationally expensive. And you might be tempted to ask, could we even efficiently detect whether or not our input data has a broken triangle? Could we find the broken triangles quickly? In other words, can we get around this n-cubed set of constraints? OK, no, probably not. OK, so in 2010, Williams and Williams proved the following lovely theorem about subcubic barriers. The following problems either all have truly subcubic algorithms, or none of them do. OK, I'm checking this list. And the second one here is checking whether a given matrix defines a metric. OK, so we're probably not likely to get around this n-cubed barrier, whatever kind of algorithm it is that we're using, whether it's lousy, naive, convex relaxation, or some other kind of algorithm. OK, so I'm going to give up on these cubic barriers. But I am interested in more combinatorial algorithms than convex relaxation. And in particular, this list of problems gives me a hint as to what kind of combinatorial algorithm I should be looking at. This all-pair shortest path. OK, all-pair shortest path problem. OK, and I'm going to keep in mind this combinatorial problem and lovely simple algorithm that's taught in undergraduate algorithms. And I'm going to go look at my metric repair problem sort of more carefully, right? I just set it up as a non-convex optimization problem. But let me go see, is there more structure in there that I could sort of separate out? And could I tackle any part of this problem with a combinatorial algorithm? Could I say something about the hardness of other parts of this problem? OK, so the first thing I'm going to do is I'm going to consider a broken triangle. 1, 2, 7. You all check that 3 is smaller than 7? Yep, okay, good. And I even bowed out this leg, so you get the idea that something is wrong with this triangle. And it's this leg is the problem, the broken leg. Let's suppose that I restrict my perturbations to be decreases only. In other words, I'm going to restrict the kinds of repairs to be decreases of lengths that are too long. Okay, so I've colored this 7 and made this guy super, super big so that you think, really I should decrease 7 to 3 and then I have a proper triangle. Okay, so I'm going to call this constraint on my perturbations the decrease only metric repair problem. Okay, so I'm allowed to perturb distances by decreasing them only. Okay, I could do something else. I could restrict my perturbations to be increases only. In other words, I'm going to restrict my attention to only increasing lengths of legs that seem too short. So here I still have 1, 2, 7, and I've bowed in the leg that's of size 1 because it seems like that is too short, right? Because 3 is still less than 7. Okay, so how about I increase 1 to 5? Now I have a proper triangle, 7, okay, check. Okay, so I'm going to look at the case when I have increases only in my perturbations. So I have decrease only, increase only. And then I have, I'm going to have a little note that, this is the same triangle, 1, 2, 7. And this decrease only solution is different from the increase only solution. And so they're really quite different problems. Okay, then I have the more general problem, which is you can either increase or decrease distances. So we don't place any restrictions on the perturbation. So for example, I could increase 1 to 4, and I could decrease 7 to 5. And 6 is bigger than 5. Okay. Okay, so these 3 repair scenarios suggest that these are 3 different, or at least 2 different kinds of problems, the decrease-only case and the increase-only case. And in fact, one of them has a polynomial time solution, and it's a lovely cubic time algorithm. Everything is known about it. It's taught to undergraduates. It's the Floyd-Warshall algorithm for all pairs shortest path. And if you go look at the innards of the Floyd-Warshall algorithm for all pairs shortest path, here's a triangle. And it says if the leg of this triangle is greater than the sum of these 2 legs on the triangle, then you should decrease the length to be the sum of the 2. i.e., the shortest path from I to j should be, i.e. the length of the path from I to j should be the sum of the paths from I to k and k to j. Right? This is the guts of Floyd-Warshall. So in fact, actually, the all-pair shortest path solution for the complete graph on n vertices with weights given by d prime, which is computed by Floyd-Warshall, is the solution to the sparse metric repair for the decrease-only case. And in fact, here, there's a picture. In case you need pictures, 1, 2, I should make that be 3. Okay? So Brickell et al. Knew that the Floyd-Warshall algorithm was important in solving the metric nearness problem, which is what they called it. And then Lala and I noticed that, in fact, actually, the solution that you get from running Floyd-Warshall on Kn with distances equal to the input matrix, then the perturbation that results from the Floyd-Warshall solution is the sparsest possible decrease-only metric repair solution. And in fact, it is the metric repair solution that is closest in any LP norm, not just L0 pseudonorm. So the decrease-only metric repair problem is lovely. It has a beautiful solution. It's a very elegant polynomial time algorithm. It's clean. You can teach this to undergraduates. Alas, fun sort of begins now. This is the easy part. Okay, the increase-only metric repair problem and the general problem are much more difficult. Okay, and you can sort of understand why they are much more difficult, because if you look at, this inequality encodes a broken triangle. This leg is longer than the sum of these two. You have to figure out which one of these two should you increase in order to repair the triangle. Okay, and you can't a priori determine which leg you should choose. Should it be this one or should it be that one? And hopefully that gives you a clue as to the hardness of the problem. Choices that you make, if you say were to march through all of the triangles and you tried to repair the broken ones, choices that you make early on may impact triangles later on in the calculation. And you can't know that without sort of calculating all of them repeatedly. Okay, so, right, just combinatorially, this seems like a difficult problem because you can't figure out which leg to fix, to repair. And the other problem, if you thought, oh, I'm going to get around to this by throwing L1 minimization at this problem, there are lots of possible L1 solutions, but few are sparse. There are approximation algorithms for increase-only metric repair. We've studied its difficulty and generalized it. Okay, so just to give you an idea of what I mean by there are lots and lots of solutions with total L1 norm 4. Just take a look at this example. I can plug in any value of x here, and I get a different solution. Okay. So I'm giving you a summary of the metric repair problem on the complete graph, and I'm going to tell you a little bit about generalizations and extensions of that work, so you can see some of the approximation guarantees and how these ideas might get used in more sophisticated data analysis problems. And so we then worked on a problem that we called graph metric repair. And instead of calculating all of the distances between my data points, i.e., instead of having a complete graph on n data points, suppose that I wanted to say, some of these data points are not at all related to others, and I don't want to measure their distances. Some of the data points I do want to connect to one another, and I'm going to put an edge and a graph between those two vertices, and I'm going to make their edge length be the distance between them. So I can generalize this problem to any graph, any weighted graph. I can generalize the notion of a triangle inequality to a chordal inequality, a broken chord. So generalize from triangles to longer chords. Okay, and so I can do increase-only metric repair on graphs. I can of course do decrease-only metric repair on graphs. The interesting cases are the increase-only and the general. And then I motivated this problem as a way of cleaning your data. I motivated corrupted data as, say, having lots of missing entries. We heard several allusions to data imputation yesterday from Andrew Lowe. So imagine not only repairing distances on graphs or distances between data points, but repairing data that are ostensibly from a manifold. So suppose I'm going to assume that my data lie on some low-dimensional manifold, and I'm trying to compute some embedding. But suppose that lots of the entries in any given data point are 0. So I have missing values in these data points. Then this manifold is going to be incredibly noisy in a very specific way, and my distances are going to just be completely corrupted. And any dimension reduction or a manifold embedding algorithm I'm going to run, the first step is to compute the distances between the points on the manifold. And if you have lots of zeros, then you're completely out of luck. OK, so these were the extensions and the generalizations. I have a bit of time to go into all of them. So I'm going to state formally. So first I'll do a little bit about graph metric repair, and then a little bit about manifold repair. And hopefully I'll end with a cool picture for the manifold repair problem. So graph metric repair, here is formally the problem. Given a weighted undirected graph G and some set of allowed values for my perturbation, find the smallest set of edges such that by modifying the weight of each edge in the set, by adding some value from the allowed perturbations, the new distances satisfy a metric on the graph. OK, does that make sense? That's the generalization from Kn to any general graph. OK? And this problem is related to matrix completion, to graph cutting problems, metric embeddings with outliers. It's related to all kinds of graph algorithms. And so we have a number of hardness results. We have a number of approximation algorithms. We understand on what kinds of graphs we can come up with what kind of approximation algorithms for the increase only and general cases. So I'm going to remind you that the decrease only case is solvable in cubic time. And we have a really, really cute proof that shows that if you if you allow even just one single number, one like alpha, as your possible increase for the edge lengths, then the problem becomes NP complete. So increase only with any, even if it's just one positive number, is a serious problem. Okay, so we have approximation preserving reductions from well-known graph problems, multi-cut and length-bounded cut to graph metric repair. We also have a nice FPT analysis, a fixed parameter tractable algorithm for when we have a chordal graph. A chordal graph is, it's k-chordal if it has chords of length k in it. So it's like cycles of length k. I'm not going to go into too much detail about this. This is a really nice paper on graph algorithms. I'm going to talk a little bit more about manifold repair because it's a little bit closer to what people do for data analysis problems. In fact, lots of people do dimension reduction for lots of different applications. And so some of my favorite examples of dimension reduction algorithms are isomap, Laplacian eigenmaps, LLE, graph diffusion. I sometimes work in computational biology, so t-SNE is a favorite, or not. It has problems. These are all examples of dimension reduction algorithms. And they all begin with the idea that, or the model that real-world data somehow lie on a low-dimensional manifold, which is embedded in a high-dimensional space. And really, the right way to get an idea of the structure of my data set is to unroll it or to embed or to somehow flatten this manifold down to a low-dimensional setting. And the canonical example that's used is the Swiss roll. I have a friend who's Swiss who says these things they're not, whatever this is, it's not called that in Switzerland. So the Swiss roll should somehow be unrolled and flattened into 2 dimensions into a rectangle. Okay? All right, and so the general structure of these dimension reduction algorithms is as follows. You have data, or you're given a distance matrix. So from your data, you compute the distances amongst all the points. And then you form some kind of graph, like a k-neighborhood graph or an epsilon neighborhood graph. And then you run some kind of manifold learning algorithm like isomap or LLE, and then you project down to a low-dimensional representation. But you know, this is all fine and good, but if your data are corrupted in such a way that this distance matrix doesn't satisfy a metric, none of this is going to work. Or nobody has stopped to ask, hey, does this work? People have looked at what happens if you add noise. Okay, so if you add Gaussian noise, there are results for dimension reduction. But what if you have missing data? What if the distance matrix does not satisfy a metric? What happens to these dimension reduction algorithms? Unfortunately, garbage is what happens to them. So in particular, if you take the Swiss roll data set and it's got 2,000 points and you run isomap on it on the original data set, you unwrap it. Oh, it looks beautiful. It looks like the unwrapped pastry that comes from Switzerland. And if you take the original Swiss roll data set and you remove, or you set to 0 a bunch of the entries so if you take, for any given data point, you set some of its entries to 0. It's a high dimensional point, set some of them to 0, so that you have corrupted, and then use those data points to compute a distance matrix. So you have a corrupted distance matrix. And then you try and run isomap on it. You get garbage. Okay, so this is the true distance. This is isomap under the true distance matrix. This is isomap under the corrupted distance matrix. And then if you run, I'm going to advertise our algorithm. If you repair the distance matrix and then run isomap on it, you get something that looks much more reasonable. It looks much closer to the true one than the corrupted one. You got to use increase only. Okay, so I'm going to go through some of the, I'm going to formally state the problem, and I'm going to tell you a little bit about some algorithms, some parts of which we can prove things about and some parts we can't. Okay, so here's the problem statement for manifold repair. So given a data matrix X and an oracle matrix Q that tells you, oh wow, cool. That tells you the IJ entry is missing. So you need to, for this algorithm, you need to know, is the entry truly missing or not? It's not simply enough to set it to 0. So anyway, suppose you have an oracle. Repair sparsely as possible, the corrupted dissimilarity matrix D so that standard dimension reduction algorithms work well or are good enough. Okay? All right. Does that make sense? That's the problem. Notice that you're not adjusting X. You're not repairing X. You're repairing the distance matrix D, or dissimilarity matrix D, that arises from X. So you're not actually filling in any holes in the manifold, nor are you actually filling in any holes in the data points. You're simply repairing the matrix that's derived from the data set. Okay, but as I said, these dimension reduction algorithms all must use a distance matrix to run anyway, so it's the right thing to do. Okay, so I'm going to walk you through an example of our algorithm, which we called MR missing, and I'm going to show you some parts that we can prove things about and some parts that we can't. Okay, so imagine that I have as my 3 data points the following matrix. This row, and this row. These are my 3 data points in R4. And I have an oracle which tells me which entries are missing. Those are the stars. So my algorithm, right, so this is my corrupted data set. And my algorithm says I'm going to compute the distances. And I'm going to use L1 for this example because that's what I could calculate on the back of a piece of paper. I didn't have to write square roots in LaTeX. So this is the L1 distance amongst these 3 points. So the distance between these 2 rows is 2. The distance between the first row and the third row is 4. And then the distance between the second and the third is 1. So that is my matrix. And I'm going to let you all verify, indeed, there is a broken triangle. This matrix does not satisfy the properties of a metric because 4 is bigger than 3, right? 2 plus 1 is smaller than 4. Okay, I have a broken triangle. And okay, so here is my corrupted distance matrix. And I know that these distances are, whatever distance is corrupted is probably smaller. I guess let me rephrase this. All of the distances are smaller than they probably are in the correct data because I have used my oracle to disregard any entries where I have missing data. Okay, so, oh yes, project 2 data points to the coordinates that are present in both. So the L1 distance here is 1 plus 1 is 2. So wherever I have missing entries, I simply disregard them in my distance calculation. And so my repairs to the distances should be increases only, because surely these distances are shorter or smaller than they really should be if my data set weren't corrupted. Okay, so that answers your question. I should use increase only. And I'll tell you, for these experiments, we used a heuristic algorithm that we can't really prove anything about, but it seems to work pretty well. There are approximation algorithms for increase only metric repair that we can prove things about, and they're really lousy, at least in theory. Okay, so, right, people usually ask me, oh, what if you set all these guys to maximum values and then try and decrease things? So yeah, there are all kinds of fun things you can try instead of this naive thing. The naive thing works actually quite well. So there are things that we can prove about this algorithm, and one thing that we can prove in a model setting is that this way of estimating the data by ignoring any coordinates where we have don't knows, that this procedure is fairly good. So what we want to show in our algorithm is that in this distance estimation step, points that are far away from one another rarely get close. And then if we do end up taking faraway points and bringing them together, that the repair step pushes them back out. So what we can do is we can prove something along these lines. And so for the sake of time, I'm going to tell you we have a model set up where we can show that this distance calculation is not too bad most of the time in this perfect setting of 2 Gaussian clouds. Okay, great. That's the one thing we could prove stuff about for manifold repair. Okay, so now I'm going to give you some of our empirical verifications of this manifold repair algorithm. And the first one is simply a visual verification. Do the pictures look good? If they don't, you have a problem. So check, they look good on synthetic manifolds. Here are 4 complete data sets. Here are the projections of the data sets where we had 40% missing data, and we corrected the distance matrices using this MR missing algorithm, and then we projected using isomap. They're not bad. Given that 40% of the original data is missing, they're not bad. You can also, visual checks are very, very far from anything that resembles mathematical proof of anything. So we decided to get slightly more rigorous, and we took a standard data set, MNIST, and we said, let's just at least check visually that if we take some number of instances, some number of images from some number of digits from MNIST, and we knocked out 70% of the original data, and then we corrected them using our algorithm, and we projected both using isomap. Visually they're not too bad. Another check is to say, how good a job can we do for classification under missing data? So suppose we knock out 0, 40, up to 90% of the coordinates in the MNIST images. How well a job can we do distinguishing the digits? Well, if you take an SVM that's trained on the low dimensional projections, and you have no data missing, so everything is perfect, you get about 94% accuracy. Not too bad. And you can see, this SVM still does a good job at classifying the digits up till about 60 to 70% of the data is missing. Well, that's pretty impressive. Okay, so my final picture, which you guys will have to ask me about offline, is, can you tell me what digits these are? So this is about 70% of the pixels missing from 4 different digits in the MNIST data. Okay, so you can't tell me what these digits are, but our algorithm will repair the distances and then do a low dimensional projection and then run SVM, and we'll get these digits correct. They are those. Okay, what you have to come see offline is that if you look at the screen at a certain angle, you can easily see that this is 3, 5, 6, 8. So there is information contained in these images, even with 70% of the pixels missing. You just have to look at it in the right way. Okay, so I'm going to end with where we're going next. We were inspired by single-cell sequencing data, which has an awful lot of missing entries, and we're working on using these ideas for metric learning. Okay, so thank you. Yeah. Oh, no, but we do have experiments. So, so no, I don't know how hard it is. I mean, of course, for decrease only, this is easy. So no, but we did do a bunch of experiments way back when we had a bunch of heuristics for increase only metric repair. So no, I don't have any concrete, theoretical results for. You get really different behavior under the different heuristics depending on the input type. So a random model is quite different. So random points in R2 or in RD is quite different from a random graph, as you might expect. And now I've forgotten any of the details of the heuristics beyond that. No. No, so the point, the question was, have we tried other classifiers? The point of the experiment was not to get super great classification. It was simply to prove that it worked, not to get great, not to improve classification beyond something kind of basic.
How can you, how do you know when you are using the decrease-only algorithm, when you change one metric, it will not disturb other, maintain other triangles?
Oh, so the answer is what's inside the proof of decrease-only metric repair?
So you just advertise the method, right? So is it available somewhere as a package, or it will be very soon?
Oh! Okay, so, well, the glib answer to that is Floyd Warshall's been developed for decades. The not glib answer is no, we do not have anything good to release publicly for IOMR, because as I said, the heuristics work really well in practice. I recall some of the details. We can prove like arbitrarily bad approximation guarantees for one of the heuristics. This much I remember. Like it can be arbitrarily bad. And we can cook up a gadget for which it's terrible, but it works fine in practice. And then we haven't even implemented the approximation algorithms because they're ugly. They're complicated, they're ugly. And it's not at all clear what makes sense in practice. Okay, thank you.